In this presentation, we'll discuss how our concept of time is modified in light of relativity theories. The Galilean transformation describes the relation between the physics of a system moving at constant speed and a system that is stationary. In this transformation, the times of a system moving at constant speed and a system that is stationary are equal. On the other hand, the theory of relativity states that the times of these two systems are different. The special theory of relativity predicts the time dilation in the moving system as compared to the stationary system. Several experiments have shown that this time dilation occurs. One of these is the muon lifetime. The muons are detected on the Earth. These particles move almost at the speed of light from space to Earth. These muons are observed to have substantially longer lifetimes than stationary muons produced in the laboratory. In daily life, we might think of the following as example of time dilation. That is, time moves more slowly for someone who is traveling at a constant speed on a bus than for someone who is stopping at the crosswalk. So you can see the difference in time between a person on a sidewalk and bus passengers moving at constant speed. Gravity, whose effect is equivalent to acceleration, is related to general relativity. The general relativity also predicts and accounts for gravitational time dilation. Time moves more slowly in systems with larger gravitational force. As an example of time dilation in daily life, we can consider followings. That is, time moves more slowly at sea level than it does at high altitudes. These time dilations, due to height differences of less than 1 meter, have been experimentally verified in the laboratory. So, general relativity predicts the time dilation of our system with a larger gravitational force. So you can see the difference in time between a person at sea level and a person on Mount Everest high altitudes. In this presentation, we will discuss time dilation in light of relativity theories. These time dilation phenomena are used in our everyday lives. Every day, when we drive, we utilize GPS. In this GPS system, we use the satellite signals to calculate our positions. The satellites are orbiting the Earth very fast and fairly far from the Earth's surface. However, the GPS receivers are essentially stationary compared to the motion of the satellites and also on the Earth's surface. Therefore, time at satellites is different from ours in light of relativity theories. We must account for time dilations while using satellite signals to determine our positions. Otherwise, the GPS system's prediction of our position won't match where we actually are. These topics relating to relativity theories will be covered in this representation. Gravitation is equivalent to acceleration. We can see this in the following phenomena. A person in a closed spacecraft noticed that the thing, when dropped, falls to the ship's floor. The astronaut believes that his craft has touched down on a certain planet, and that the object is falling because of the planet's gravity. However, when the spaceship is accelerating upward, the object may also be falling to the floor. Now imagine that when he drops the object, it floats at rest rather than falling. In this instance, he believes that his spacecraft is somewhere in space, so no gravity. However, the same event can be seen while the spacecraft is falling freely because of the planet's gravity. So, you can see that the object is affected in the same way by gravity and acceleration. As a result, the gravitation pull and the acceleration are equivalent. So in both accelerating spaceship and a spaceship on a certain planet situations, when we drop an object inside a closed spaceship, it drops to the floor. As a result, gravity and acceleration are equivalent. Imagine that the light is coming into the space through the small window. When a spaceship is in a gravity-free space, light enters the spaceship horizontally. Okay, so in this way. The equivalence principle states that the same thing will be seen when a spaceship is falling freely because of the planet's gravity. Now, we can see that the light entering the spaceship is bent as a spaceship accelerates. The light is bent this way. The equivalence principle states that the planet's gravitational field also bends the light entering the spaceship. Okay. As a result, we can see that when light travels through the gravitational field, it is bent. Okay. Gravity causes space to distort, according to general relativity. The space is thus bent close to the planets and the stars that provides gravity. There, the light seems to have been bent. However, in the warped space, the light actually follows the shortest path. Now let's see the time dilation in special relativity. The stationary person observes that time in the system moving at constant speed relative to him moves more slowly than it does in his own system. So this is a stationary portion as moving portion. This phenomenon, which occurs in a moving system, is known as time dilation. This indicates that the rest frame's time interval is longer. Time interval is longer than the moving frames. Okay, which is expressed as delta t and delta t prime time interval. Delta t is time interval in the stationary system, and delta t prime is time interval in moving system. Since this gamma is greater than 1, because the speed can be less than the speed of light, so delta t must be greater than delta t prime. So time interval in the stationary system is larger than that in moving system. So for example, while a year in moving system passes in the spaceship, 3 years pass on Earth. So time interval in the stationary system is larger than that in the moving system. So this is called time dilation in the moving system. So it can say that time moves more slowly in spaceship. Okay. As the spaceship's speed approaches the speed of light, the time difference between Earth and the spaceship increases. The time interval for a system whose speed is substantially slower than the speed of light is given as, we can approximate this equation to this form. Okay. The time intervals of the moving and the rest of systems are here denoted by delta t prime and delta t respectively. So the equation for time difference between two systems is this one, right? So this is time difference between two systems. The moving system's clock runs this much slower than the rest of systems. Okay. Let's see the example. On a flight from Seoul to New York, 14 hours pass for portion on the ground. How much time passes for the passengers on an airplane? Let's say that 300 meters per second, that corresponds to 90 degrees of speed of sound, is the average airplane speed. The time difference between being on the ground and in the air is calculated as 25 nanoseconds. Okay. So we use the delta t here, 14 hours. Therefore, time in an airplane thus passes 25 nanoseconds more slowly than it does on the ground. Okay. So very small, but there is time difference between two systems. Let's see another example. Assume the future spaceship can travel at 90% speed of light. The spaceship travels to the planet that is 30 light years from Earth. How much time passes in the spaceship while traveling to the planet? The time interval between the Earth and the spaceship is expressed as this equation. If we put speed of 0.9 c, then we can obtain delta t prime in spaceship as 0.44 times the time interval on Earth. As a result, just 44% of the time on Earth is spent in the spaceship. When you put delta t 30 years, we can obtain delta t prime 13.2 years. Therefore, while 30 years pass on Earth, the spaceship only travels through around 13 years. Now let's see the speed of spaceship, the present spaceship speed. We need the escape velocity from Earth, that is 11.2 km per second, and the spaceship escape from solar system in G's the speed, so that is escape velocity of the spaceship from the solar system is 16.26 km per second. In the year of 1977, Voice 1 and Voice 2 was launched, and this Voice 1 and Voice 2 escaped from the solar system in the year of 2013 and 2018. So this Voice spaceship, the speed was exceed this escape velocity from the solar system. Now let's see the gravitational time dilation. The spaceship accelerates upward. The light is emitted to the ceiling by a laser at the spaceship's floor. Then the Doppler effect causes the observer at the ceiling to observe the light's redshifted wavelength, since he is getting away from the incoming laser light. On the other hand, the floor observer is getting closer to the coming laser from the ceiling, and thus observes the laser light's blue shifted wavelength. So the observer at the ceiling observe the red shifted wavelengths. On the other hand, observer at the floor observe the blue shifted wavelengths of laser light. According to the equivalence principle, we can apply these results from the accelerating spaceship system to the spaceship that has landed on a planet. The observer above the ground at the ceiling here, where there is less gravity here, right? So the observer above the ground, where there is less gravity, observes the laser light's red-shifted wavelength coming from the ground here, where there is more gravity. For someone standing on the ground, where there is more gravity, observes the light's blue-shifted wavelength coming from above where there is less gravity. So this phenomenon is known as gravitational redshift. Since the spacecraft is traveling upward, someone who is on the ground observes the blue shifted signal, while the observer on the ceiling here sees the red shifted signal. The relationship between the frequency and the wavelength is inverse. So long redshifted wavelengths therefore have smaller frequencies corresponding to shorter time intervals. Therefore, time moves more slowly on the ground due to the smaller time interval seen at the ceiling. Conversely, the longer time interval at the ceiling, shown by the blue shifted signal seen at the floor, implies that time moves faster at the ceiling. Assume that the same lasers are installed on the ceiling and the floor. The observer at the ceiling is provided with a very accurate frequency detector. He operates the detector for just 1 second to measure the frequency of the laser light coming from the floor. He measures the frequency of laser light at the ceiling for the same 1 second. So he compared two frequencies. Gravity causes laser light coming from the floor to be redshifted. Thus, he observes that the ceiling located laser light has higher frequency than the laser light coming from the floor. These observations lead him to the conclusion that the clock at the ceiling runs faster than the clock at the floor. The floor observer may observe the same results. The floor and the ceiling observers both agree on the same observations. These results imply that time runs slower on the ground, where there is more gravity, than it does at the ceiling, where there is less gravity. This shows how gravity affects the flow of time. Where there is more gravity, time runs more slowly. This phenomenon is known as gravitational time dilation. The gravitational time dilation can be written as this relationship. Here, delta t prime represents a time interval in a frame close to a gravitational source, such as planet, and delta t, the time interval in a frame far from the gravitational source. And the r, m, and z denote the distance from the gravitational source, the gravitational source's mass, and the gravitational constant, respectively. Now let's see the example from the concept here. A spaceship is launched toward a planet that is close to the black hole to see if it is suitable for human habitation. This planet is close to the black hole. Since commencement here is considered to be far away from the black hole's gravitational pull is absent here. The gravitational direction increases as the spaceship gets closer to the planet near the black hole. Let's say planet's distance from the black hole is equal to that of the Sun from the Neptune in our solar system. And the black hole has mass that is 6.6 billion times larger than that of the Sun. What will be the time dilation in the spaceship be when it lands on the planet? This is the our Sun's mass. So black hole has the mass that is 6.6 billion times larger than that of Sun. So we can get mass of black hole, this value. And the distance between planet and the black hole is equal to that of Sun from Neptune in our solar system that is given here. And G is gravitational constant. So if we put this one here, then we have delta T prime equal to delta T of half of delta T. As a result, the spaceship's time interval is half that of the command ship. Okay. The time duration resulting from special relativity should be included if the spaceship is moving at speed that is near to the speed of light. Now let's see the time dilation difference due to altitude. The time interval at a specific altitude r that corresponds to 1 second at the place where there is no gravitational pull from the mass m is expressed as deceleration. By inserting delta t equal 1 second into above equation, we obtain this relationship here. We put delta 1 second, we can have this relationship. As a result, the time interval at altitude Ra and Rb is given by this relationship. So this delta AB represents time interval difference between the place of altitude Ra and altitude Rb. The conclusion is that time runs more slowly at low altitude than it does at high altitude. So time runs slower at the sea level than it does in the mountain region. Now let's see the example. Find difference in lifespan between persons who live at the sea level and those who reside in 3,000 high alpine regions due to the consequence of time dilation. If you use the relationship, this relationship, here Ra is the difference from the center of Earth to the surface of the Earth. So that is the radius of Earth. And Rb is alpine region. So Rb is equal to R radius of Earth plus the altitude 3,000 meters. So you can get this number. The time indicated above, this one, this value, represents difference in time between sea level and the alpine region per 1 second. Okay. At the sea level, the time interval is this value per second longer than it is in the high alpine region. There's time difference per second, for 1 second. So daily time difference, we can get 28.3 nanosecond. And the time difference per life is computed as 0.8 millisecond for an 80-year lifespan. As a result of gravitational time dilation, people at sea level live 0.8 milliseconds longer than those in alpine regions at altitude of 3,000 meters. This is very small value because the gravitational difference is very small. Now let's see how relativistic time dilation is applied to the GPS system. GPS system is the global positioning system. We are able to determine our precise location and the time anywhere on the Earth with the help of the 31 satellites that makes up GPS. They are necessarily affected by the time dilation because they move at tremendous speeds in contrast to us and are further away from the gravitational field source, that is Earth. We can determine our location by knowing the distance between the GPS signal receiver, such as a smartphone, and the 3 satellites. This method is known as trilateration. If you know the distance between the GPS receiver and the satellite, 3 satellites, then if we draw the circle of the 3 satellites, and the intersection is the position of the our receiver, GPS receiver. So this method is called the trilateration. If the distances between the receiver, GPS receiver, and the 3 satellites are calculated using signals from 3 satellites, the position of the receiver will be the intersection of the 3 satellite circles, as illustrated in this figure. Trilateration is the term for this process. Typically, signals from more than 3 satellites are used to determine the receiver's position for time correction. The altitude of the satellite is about 13,000 kilometers. So the distance from the center of Earth to the satellite is about 20,000 kilometers. And the speed of the satellite is about 3,800 meters per second. In comparison to the GPS receiver, which is installed in a car or ship moving at a relatively slow speed, the satellites are orbiting the Earth at very high speed. Therefore, according to the special relativity, time moves more slowly in satellites than it does in a car or ship with a receiver. Time intervals in the satellites and the receiver are related by the expression. This expression. So if we put the speed of satellite, then we can get this number. So as a result, time in the satellites runs at rate of 8.35 to 10 to the minus 11 seconds per second slower than in the receiver. Thus, the satellite's time duration is 7 microseconds per day. If we multiply this number by 360 seconds, 3,600 seconds, and 24 hours, so it's 4 per day. Okay. Next, the satellites are 13,814 kilometers above the surface of the Earth. As a result, the gravitational pull of the Earth in the satellite is less than in the receiver on the surface of the Earth. Time runs faster in the satellite than in the receiver, according to the general relativity. The time duration is expressed by general relativity as this duration. Here, the GPS receiver is located on the surface of the Earth, so the distance between center of Earth to the GPS receiver is the radius of the Earth, and satellite, the altitude is 13,814 kilometers, so the distance from the center of Earth to the satellite is 20,184 kilometers. So if you put these numbers, then you can get this time difference. Therefore, time runs 5.07 times 10 to the minus 10 seconds per second faster in satellites than it does in the receiver, GPS receiver. The daily equivalent is 45.85 milliseconds. So according to general relativity, time in the satellites runs 45.85 microseconds faster than it does in the GPS receiver each day. However, according to special relativity, we already calculated, time in the satellites move 7 microseconds slower than it does in the receiver every day. So, as a result, according to relativity, time in the satellites moves 38.85 microseconds faster than it does in the GPS receiver each day. So time difference between satellite and the GPS. So we have to consider this difference, time difference, to communicate between the satellites and GPS receiver. So as previously demonstrated, the time dilation caused by relativity in the satellite is given as this number per 1 second. If satellites use a microwave signal at frequency of 10.23 megahertz to communicate with the base station on Earth, the satellite's microwave frequency needs to be adjusted. So you have to subtract this number and multiply this frequency. Then we can get the frequency of this number to compensate for relativistic time dilation. So, in order for the satellite clocks to run in synchronization with the 10.23 megahertz clocks on the ground, they have been set to run at this frequency. Then we can correct the time dilation caused by the relativity.